So you might remember that when we talked about double integrals, we said that there are two different types. There's double integrals of type 1 when you're cutting vertically first, and then double integrals of type 2 when you're cutting horizontally first. So somehow it shouldn't be a big surprise to you that with triple integrals, there's going to be three different types. Now, I want to make something very clear when it comes to how you set up triple integrals. Okay? The first cut for triple integrals is always going to be a 3D cut, a cut in space. So you can cut in the z direction, in the y direction, or in the x direction. All right? The second cut and the third cut, the other two cuts, are going to take place in the projection of your three-dimensional object into one of the coordinate planes. And so which coordinate plane you project into is determines what type integral you are. This is going to feel a little overwhelming at first, but just like all things mathematics, with a little bit of practice, you'll become comfortable with it. So let's look at type 1. So a type 1 integral you can think about as one where you can project it easily into the xy plane. More specifically, it's a 3D solid. You're integrating over a solid. That's what triple integrals are always over, right? Triple integrals are always over solids. I'm integrating over a solid where there is a bottom surface that's z equals some function of x and y, and then a top surface, z equals some function of x and y. In other words, you can make a vertical cut parallel to the z-axis from a bottom surface to a top surface. When you can do that, then this is type 1. One more thing. The region D that we're shading, think about that as the projection of your solid down into the xy plane. So imagine if you could float in zero gravity, how fun that would be. And then imagine floating over the surface and looking straight down. And I'm not saying that D is necessarily equal to this bottom curve or this top curve, but whatever, maybe the solid kind of bulges in the middle, whatever you would see from up here looking down, imagining just projecting it into the xy plane, that's what D is. Let me erase my line because I don't really like it too much. Okay, so this is all fine and good. How does one actually set up a triple integral like this? Let's do it. So if you want to have the triple integral over the solid, the blue solid E of some function f of x, y, z, dv, you first set this up. Let's just do three integrals. Okay, going to write down my function f of x, y, z, and then here's the deal. Type 1, you cut first vertically. I'll think of it vertically, which means in this case parallel to the z-axis. I'm cutting along the z-axis. I make a z-cut. That's what type 1 is. All right? Z goes from u1 of xy up to u2 of xy. And then here's the scoop. There's two more integrals to fill out. There's actually different ways you can do that. Those integrals are just over the two-dimensional projection D. And you have choices. You can cut it dx dy or dy dx. So we typically, to capture this, we'll just say double integral dA and then a single integral dz. And that's what a type 1 integral looks like. That's how you set it up. All right, so one more time. Type 1, you're projecting into the xy plane. The bounds that go here are functions of x and y. Maybe there's no x's, maybe it's just y's, but you can't have z's here, right? It's z equals x and y, z equals x and y, and your first thing that you integrate, your first variable that you integrate with respect to is z. So you start out with a dz, and then you can choose what the other two are. That's what type 1 is. Now, type 2, some people don't like the different numbering, whatever. Type 2, we're going to cut along the x-axis. Keep in mind, x is starting at 0 and it's going this way. So we're going to cut that way when we do this, right? I'm starting here with a function of y and z, and then I'm going to, I hit another function of y and z. So type 1, you cut vertically in the z direction first. Type 2, you cut along the x-axis first. And again, there's a projection involved. If you were standing over here and you were looking that way, you would actually see, if you could kind of squint and project this thing onto the YZ plane, you would see that solid D. So let's take a moment and write down the associated triple integral. I would encourage you to pause the video and see if you can do it yourself, and then we'll do it together. So the triple integral over E of f of x, y, z dv, this becomes still a triple integral, but now I'm thinking in terms of x first. My cut was x, so I'm going to do a dx integral first. X goes from u1 of yz up to u2 of yz, and then I'll just put parentheses here. I don't know what you're going to do with the other two. Those are just however you choose to cut it over d, and we'll put a dA. And just to be clear here, I should have done this on the previous one. This dA will either be a dy dz, or it might be a dz dy. You get to pick. I think for the sake of the notes, we should go back on this one and point out that this will either be a dx dy or dy dx. There we go. Okay, so again, these bounds will come from two-dimensional cuts on D, and you'll get to pick those. And as I said earlier, we'll learn these best by doing examples together. But I've got to give you some basic setup here. So type 3 is the last one. You can kind of guess it all by now. You're going to cut along the y-axis. So I'm going to cut parallel to the y-axis. I'm going to start at a y value and then go out to another y. My first y is some function of x and z, and my second y is another function of x and z, and that's what allows me to make those nice cuts. If I was standing here looking that way, then I would see this projection D, and that's the region that we're going to be able to set up the other two integrals over. So let's go ahead and write down the associated triple integral. So triple integral over the solid E of f of x, y, z dv. This is equal to, pause the video real quick, see if you can do it. This is equal to, we're going to first cut with respect to y. Y goes from u1 of xz out to u2 of xz. And then I'm going to have the other two integrals are over this region D, dA. All right, so those are the three types. So I thought in the next part, we will do an example coming up with the projection. How do you actually visualize it, and how do you actually write it down? And then at some point very soon, we'll start working out